Okay, we're continuing on here, chapter 8, and last time, obviously, we talked about still grams to moles conversions. And as we talked about, and as we've done before, again, a reminder, that conversion of grams to moles are backwards, again, is the molar mass that we get from the periodic table. And that is our grams per mole, which again can be used basically as a conversion factor to go between those. We finished up last time talking about kind of two types of formulas, the molecular formula and the empirical formula. And the molecular formula tells you exactly what's present in terms of the elements and the atoms of each of those things. The empirical formula is the simplest whole number ratio of what's present. So again, if we have something like here, C4H8 as our molecular formula, that is again a 4 carbon to 8 hydrogen relationship. And that's the same as you could divide everybody by 4 here and end up with still whole numbers of C1C for every 2 hydrogens. And that would be basically our reduced down empirical formula of CH2 would be our empirical formula. So if you have the molecular formula given to you and you want the empirical formula and you look at the subscripts on the bottom there and you can reduce them all down by a common number, and the key there is you guys still have whole numbers, you could get to your empirical formula. A reminder as well that sometimes the molecular formula and the empirical formula are the same. Again, something like water is a very common sort of example. That's obviously our molecular formula. But again, that's 2 hydrogens for every 1 oxygen. There's no way to reduce that down any further and still have whole numbers. So that would be both its molecular formula and empirical formula. And as we also talked about ionic compounds, when we put together positive ions and negative ions, those are also empirical formulas because the way we put them together is the simplest way to get to 0, the positive charge and the negative charge. Any questions on any of that there? Okay. All right, so let's continue on where we kind of left off there. Again, as I just mentioned, many molecules, the empirical and molecular forms are the same. So water's another example. Again, ammonia here, which is 1 nitrogen for every 3 hydrogens. There's no way to kind of reduce that down and get any all whole numbers. Same thing here, like CO2, that's 1 carbon for every 2 oxygens as well. Thank you. Yeah, thanks. So why don't you take a moment for each of these and write what the empirical formula should be if these are the molecular formulas. Okay, let's take a look on the first one here. We got basically 2 carbons for every 2 hydrogens. That's basically a 2 to 2 relationship, which you can reduce down to a 1 to 1 relationship, which means that our empirical formula here would be CH. As again, you can divide each of these by 2 and still get whole numbers. Take a look at the next one. That's 2 iodines for every 5 oxygens. That'd be different. That's basically a 2 to 5 relationship. And again, at this point, there's no way to reduce that down any further and still hit whole numbers. So this would also be its empirical formula, as that is the simplest sort of reduction of that formula. Lastly here, we got 6 carbons for every 12 hydrogens. For every 6 oxygens, that's a 6 to 12 to 6 relationship. Here we actually can divide everybody by 6 and get a 1 to 2 to 1 relationship here. And that would then give us a CH2O as our empirical formula there. That one. Any questions on that there? So again, if you're given the sort of the molecular formula and just want the empirical, all you simply have to do is reduce down those subscripts. And again, they still always on the bottom here needs to be whole numbers. Yeah, so all those guys need to be whole numbers. All right, let's talk about another sort of idea, and this is the percent composition by mass. And the percent composition by mass, the formula tells us the composition of the compound, and we can calculate the percent composition by mass by taking each element and divide it by the molar mass of the compound. So to find the percent of the element, you basically take the mass of that element in the compound. It's basically the molar mass of that particular element divided by the molar mass of the compound. And I ran out of room there, but times by 100% there. So times it by 100%. And that should be multiplying there. Multiplying. All right, so let's take a look at one here, perhaps. And let's say we had hydrogen peroxide, which is obviously a molecular formula here, and we wanted to calculate the percent composition of each of these elements. The first thing we would want to do is get the molar mass of this compound. So to get the molar mass of this compound, obviously we need to go to periodic table and find our elements. So we look up oxygen, we look up hydrogen, and we would add this together. So this would give us 2 times hydrogen molar mass from the periodic table plus 2 times oxygen's molar mass from the periodic table. And that's going to give us here a molar mass for hydrogen peroxide of, looks like 3402. So now we want to figure out the percentage of each element. So we can do the percentage of hydrogen. Now to get the mass of hydrogen in that compound, since there are 2 of them, we do need to get the mass of the 2 hydrogens. And we need to divide it by the molar mass of the entire compound that we just calculated and times it by 100%. So if we do that, that's 2 times 1.008 or 2.016 divided by 3402 times 100. Will give us that by mass, hydrogen peroxide is about 5.926% hydrogen. So it's made up of about 6% hydrogen in this case. We could do the exact same thing here for our oxygen. There's also 2 oxygens in that formula, so we'll take 2 times the molar mass of oxygen, which gives us about 32, divided by the molar mass of the entire compound, which is 34 and some change, times it by 100%, and that's going to get us here 94.06 percent. And if we add that up, that's approximately 100% of the entire compound. So this is mainly made up by mass of oxygen. So oxygen is the most mass of this particular compound, and about 6% there of hydrogen. By the way, because these were the only 2 elements present, I could have, if I wanted to, instead of calculating the percent composition of oxygen like I did, we could have also just subtracted. So we could have alternatively for the second guy find the percent of oxygen, because these are the only 2 present, 100% total minus the 5.926%, because that's the percentage of hydrogen. And we'll get up there. That'll get us to about our 94.06. So at that point, you can just do that. If you have one of the elements left and you're already figured out the percentages of the other, you can take 100 minus those, or just calculate individually like we just did there for the oxygen. Any questions on that there? All right, so why don't you try one here? Why don't you try the empirical formula for hydrogen peroxide, which is HO. So see what you come up with. The percent composition of Okay, so let's take a look. So in this case, we're looking at the empirical formula, and we'll get the molar mass of it like we did the other. And that will give us, in this case, only one hydrogen at 1.008 and one oxygen at 16 grams per mole. And that's going to get us there. We'll call it 1701 maybe. 17.01 grams per mole. Now that we have the molar mass of the entire compound, we can find our percentages of each of these elements. So our percent of hydrogen, in this case, on the empirical formula, we only have one, so 1.008 grams per mole over our 1701 grams per mole times 100%. And that is going to get us here basically 5.927%. And if we do the same thing for our oxygen, in this case, oxygen, there is one oxygen divided by 1701 grams per mole times 100%. And that will get us here about 94.06% oxygen in this case. First off, any questions on the calculation here? Now, since this is actually the empirical formula for our molecular formula that we looked at on the previous page, we do see that our percent composition by mass in our empirical formula is about 6%, just under 6%, 94%. And in our empirical formula and our molecular formula, basically just under 6% and 94%, they are the same percentages. And that makes sense because the empirical formula is just the simplest ratio of what's present in the molecular formula. So the mass composition of each of those elements are still going to be the same. So if you know the percent composition of the molecular formula, it should be the same as the empirical formula because the empirical formula, again, is just the simplest whole number ratio of that molecular formula. Any questions on that there? All right, let's try another one here. Let's do phosphoric acid. What is the percent composition of each of the elements? So hydrogen still 1.008, oxygen is 16, and phosphorus there 3097. Take a look. Again, we're going to look for the percent composition of everybody. So the first thing we really need to do is get the molar mass of our compound here. So in this case, there's 3 hydrogens from the periodic table, 1.008 for the hydrogens. There's 1 phosphorus at 3097. And there are 4 oxygens, each at 16. Again, molar mass from the periodic tables where we grab all that. That adds up to about 97.99 grams per mole. Now that we have the molar mass of the entire compound, we can take each element and get the mass of how much of that we have. So we do percent hydrogen. There are 3 hydrogens. So up on top would go just the mass of those 3 hydrogens from the periodic table divided by the molar mass of the entire thing. And again, times it by 100% here, going to get us, looks like, go 3.086% hydrogen. So it's basically made up of about 3% hydrogen by mass. We can do our percent of phosphorus. Since there's just 1 phosphorus, 3097 up on top for the 1 phosphorus, divided by the molar mass of the entire compound times 100%. That's going to get us here. If I don't divide by 1,000, there you go. Gets us about 31.61% phosphorus. And lastly here, our percentage of oxygen. There are 4 of them, so we'll take 4 times 16 for the 4 oxygens, divided by the molar mass of the entire compound. And again, times it by 100%. And that's going to get us here. About 65.31% oxygen. Again, alternatively for that last one, you could have added these together and then took 100 minus what you got there. And that would get you down here, since that was the last one that was present. And again, we should add up to about 100%. So we got 65 and 31 and 3. So that's about 100% in this case. Any questions on percent composition by mass? So straightforward is pretty much just the mass of the elements in the compound divided by the entire mass of the compound times it by 100. All right, so that brings us to then how to calculate an empirical formula. And to actually calculate the empirical formula, if you are not given the molecular formula, there are a few steps that you want to do, which we sort of talked about the other day. The first thing you want to do is take whatever they give you and get it into grams. So very commonly, if you have the percent composition by mass like we just were calculating, you could assume 100 grams. And what that will do basically is just turn your percentages into grams. So for example, if you had 52% carbon, that in that situation would mean that you would have 52 grams of carbon. So that's very common in empirical formula problems that you're given the percent composition by mass. And if it all adds up to 100%, you could assume 100 grams and just turn those percentages into grams, and then you're good to go. You're going to then take the grams of each element and you're going to convert it into moles of each element. And that obviously is what we've been doing using the molar mass, right? Is our conversion factor to do that from the periodic table, those grams per mole. Once you have the moles of each element, you're going to divide by the smallest number of moles. So again, for example, if after step number 2, you ended up with 2 moles of A and 6 moles of B, here 2 moles is the smallest number, so you would divide both of these guys by the 2 moles. That would give you 1 for A, and in this case, 3 for B. And if you hit whole numbers at this point, that would represent your empirical formula. So if you hit some whole numbers there, are pretty darn close to whole numbers, maybe like just under or something like that, 2.98, 2.99, or just over 3.02 or 3.01 or something like that, then you would have your empirical formula. But if you get to this step and you do not get whole numbers, so for example, again, if we had 2 moles of A at this point and say 5 moles of B, when we divide by 2 moles here, that will give us 1, and that will give us 2.5. And that would give us an empirical formula of AB 2.5. This is not good because it cannot be a decimal. It does have to be a whole number. And this is too far to round. And this is too far to round to a number. So again, what you have to do is kind of figure out what you can multiply that by to end up with a whole number. And in this case, you can multiply it by 2 and you will end up with a 5. That's a whole number. You would then take that factor of 2 and multiply that empirical formula by it. And that's everybody in the empirical formula. So you would end up with A2B5 as your proper empirical formula at that point once you do that. So common endings, I would say that you do come across a lot. That's kind of too far around, 0.33, 0.5, maybe a 0.25 or a 0.75, something like that. So if you got these too far to round, and really in a sort of textbook problem or a book type problem, if it's really not like super close to that whole number, you really shouldn't be rounding. You should kind of be finding a factor to multiply. Again, like I said, if it ends up with something like 2.01, that's good. You can round that to 2. If you end up with 1.97, that's probably pretty close to 2. You could round that, or 1.99 or something like that. But again, if it's kind of ending with these type of numbers, those are definitely too far to round. Any questions on any of that there? All right, so let's take a look at one here. Let's say we wanted to calculate the empirical formula here for this compound. And we have that it is basically 40.92% by mass carbon. It is 4.58% by mass hydrogen and 54.50% by mass oxygen. So in this particular case, you definitely, because you're given the percent composition of each of the elements, you definitely just want to take a quick look at all the percentages and once again make sure that it does add up to about 100%. It doesn't necessarily have to be perfectly 100%, but pretty darn close to it. And here we got 54 and 40, which is about 54. And we got about another 5, which is about 59, and 54 and 5 there is going to get us 9. I can say that right. 94 and 5 gets us about 99 plus the little extra left over there, which gets us to about 100%. So we're definitely about 100% here. And that means we could assume 100 grams. And the reason we assume 100 grams is basically it doesn't change any of the numbers. It just keeps the numbers the same. So it makes it easier. All you have to do is just take the percentage and make them into grams. So if we assume 100 grams, we would have 40.92 grams of carbon. Again, number stays the same, just turns them into grams. 4.58 grams of hydrogen and 54.50 grams of oxygen. So that's sort of our first step, is to get everybody into grams. Our next step is to convert each of these into moles. So we would go to the periodic table, and on the periodic table we see for carbon there are 12.01 grams per mole of carbon. For hydrogen it is 1.008 grams per mole. And for oxygen, it is 16 grams per mole. And again, this is basically the second step, and that's the periodic table. Again, molar mass, where we grab that from. So we take 40.92 divided by 12.01, gets us 3.4072 moles of carbon. We take 4.58 divided by 1.008, gets us 4.54, I'll call it 37 moles of hydrogen. And lastly, 54.5 divided by 16, 3.4063 moles of oxygen. And again, this is basically our second step there, convert everybody into moles. Any questions on that so far? At this point, we're going to compare the moles of each element, and we're going to be looking for the smallest always here. In this case, they're pretty darn close, but it does look like maybe oxygen just beats out the carbon. So we're going to divide everybody by the moles of oxygen in this case. So we're just going to go back through and divide everybody by those moles. And in obviously the case here of oxygen, it gives us a 1. That pretty much there gives us a 1 for the carbon. And lastly here, and again for that we got 1.0002, which is a 1. 4.5437 divided by 3.4063. And that's going to give us 1.33 here for our hydrogen. That would give us an empirical formula here of CH1.33 and O. And as we just talked about, that right there is a problem. That is not good because it's not a whole number. So here, this again is too far to round. You cannot just round it. So we need to figure out, a number to multiply that by to get to a whole number. So if we take 1.33 and times it by 1, we get 1.33. Take 1.33 and times it by 2, that's 2.66. Not quite a whole number. 1.33 times 3 gets us 3.99. That is pretty darn close to 4. Again, that's pretty close to round. So in this particular case, what we can do is we're going to take that factor of 3 and we're going to multiply everybody by that number. And that will give us C3H4O3 as our proper empirical formula. Any questions on that there? So again, you may not always get a nice whole number for everybody when you do the dividing part. You do have to sort of figure out how to clear it with a common number to multiply everybody by. Obviously, this was our third step there along the way. Any questions on those steps there? All right. So why don't you try one here? What is the empirical formula of a compound that had a total mass of 1.078 grams, and it contained 0.54 grams of sulfur, 0.538 grams of oxygen. Sulfur is 3207. Oxygen is still 16. So give that a go, see what you come up with. Okay, let's take a look again here. We want to follow our steps. We are given in this case actually the mass of the compound, which is our 1.78 grams. It's really the mass that we started with. And we're told that we have 0.540 grams of sulfur, and we also have 0.538 grams of oxygen. So this is really the total mass of our sample. And out of that sample, we have this much of each of these elements. What you definitely would probably want to do in this case is just give it a quick add and make sure it does equal that number, and it does in this case. So we're not missing any elements or anything like that. Again, if you added those numbers up and you didn't get 1.078 grams, then that would mean you were missing something, some type of element. There would probably be some more information to allow you to maybe figure that out. But let's just say, for example, you did add these up and it didn't add to them, and it told you there was another element present, you could then subtract the difference, right? And that would give you the missing element. So sometimes that it can occur. But in this case, since we have basically 100% of everything, we're ready to roll into our sort of steps for our empirical formula. And in this case, it's already in grams, so we don't have to undo it. So you definitely don't want to undo anything. So at this point, what we're going to do is just convert those grams into moles. So we're going to take our grams of each element. We're going to go to the periodic table, get the molar mass for each of those. 3207 grams per mole for sulfur and 16 grams per mole for oxygen. We're going to divide that out. Gets us 0.540 divided by 3207. Gets us something like 0.01683 moles of sulfur. 0.538 divided by 16. 0.03363 moles of oxygen. Here again, we're always dividing by the smallest. So in this case, it looks like sulfur wins. So 0.01683 moles and 0.01683 moles here are 3 moles. And that's going to give us obviously 1 for the sulfur there. And if we divide out our other one here, 0.01683, gives us about 1.99, which is pretty close to 2 in this case. So again, this is close enough to round. Obviously, 0.33 too far away. Now, at this point, that means we hit all whole numbers. So our empirical formula in this case should be SO2 in this case. Any questions on that there? So again, typically in book problems, it's got to be something like that as being close to that whole number in order for you to round, or just above it as well. So for example, if we get something like 2.01 or 2.03, that also would be close enough to round it to. Any questions on those steps there? All right. Let's try another one here. What is the empirical formula here? We got 49.3% carbon, 6.9% hydrogen, and 43.8% hydrogen. And percent compositions by mass. Once again, always good idea just to kind of add these guys up, and it does come to about 100%. So again, we know we're not missing anything. Again, if you were adding the percentages up, it didn't come to 100%, and they told you maybe a different element was also present, you can subtract from 100 to figure out the percentage of the missing element. So again, sometimes that does occur. So since we do have 100% here, we could assume that we have 100 grams. And again, the basis of that is just going to keep these numbers the same, so we don't have to do any type of changing. The only difference is we're just going to turn them into grams instead of percentages. So 49.3 grams of carbon, 6.9 grams of hydrogen, and 43.8 grams of oxygen. Once again, here we're just going to convert them into moles. So periodic table to do that, 12.01 grams per mole for carbon, 1.008 grams per mole for hydrogen, and a 16 grams per mole for our oxygen. So that's going to now give us moles of everybody, and in this case it looks like 49.3 divided by 12.01 going to get us, we'll call it 4.1049 moles of carbon, 6.9 divided by 1.008, 6.8452 moles of hydrogen, and lastly 43.8 divided by 16, 2.738 moles of oxygen. Any questions so far up to that point? So once we've done that, again, kind of like your first step, second step is to find the smallest number of moles. In this case, it is oxygen that is the smallest, so 2.73 moles gets divided by everybody. Everybody gets divided by that number. And if we do that, obviously we do get 1 for our oxygen here. For our hydrogen, 6.8452 divided by 2.738 looks like 2.5. And for our carbon, 4.1049 divided by 2.738, about a 1.499, which is pretty close to 1.5 in this case. So based off of our sort of dividing, that would get us an empirical formula of C 1.5, H 2.5, and in this case, O. As you hopefully know by now, both of these are not so great, and we cannot leave them like that because they're not whole numbers. Also, once again, too far to round here in a textbook. You can take either one here. We'll go with 1.5 and see what that does. 1.5 times 1 is 1. 1.5 times 2 is 3. So that seems like a whole number. So we can multiply this empirical formula by 2. So if we take this basically and multiply it by 2, that will give us a formula of C3H5O2. And again, in this case, this factor works good for both of them. It fixes both of them, obviously, if you multiply it by 2 as well. So it gives us our proper empirical formula of C3H5O2. Again, when you do find that factor, you want to make sure that you're multiplying by the number and not the result. So sometimes people mess up and multiply by 3 here rather than the 2. And you also want to make sure you multiply everybody by that 2, not just the one that needs fixing and stuff like that. Any questions on how to calculate an empirical formula here? All right, so this is how we calculate empirical formulas. As we also talked about, there are molecular formulas, and there are a process that we use to calculate a molecular formula. And to calculate a molecular formula, there's really 3 things that you need. You need the empirical formula, and that can either be given to you in a problem or you need to calculate it like we've been doing. So I would say in most cases, you'll have to calculate it like we've been doing to get to the empirical formula. Once you do that, you need the approximate molar mass of the compound. The good news on this one is it is usually given to you in the problem. So somewhere in the problem, they'll say, hey, the molar mass of this compound is 180 grams per mole. They may also not give you an exact number. They may give you like a range, like, hey, it ranges from like 100 to 110 grams, somewhere in that ballpark. And if they do give you a range, you could either use kind of like the low end of the range they gave you. You could use the high end of the range. You could take the average number in the middle of those numbers and use that as the molar mass. So a lot of times that's given to you, and sometimes it's just straight up a number, or it may be like a range of numbers, like again, 100 to like 110. So if you're going to do that calculation, you can either use 100, use 110, or you could kind of average a number in the middle there and use that one as well. They all will come out to basically the same thing. The last thing you need to know is the molar mass of your empirical formula. So the empirical formula, molar mass, I'm not sure where that went, but the molar mass of your empirical formula. So what you do with those numbers is you take the molar mass that they gave you in the problem and you divide it by the molar mass of your empirical formula, and this will give you a number. And that number is what you multiply the empirical formula by. So this number is what you would multiply the empirical formula by. So let's just say, for example, you did this and you got a 4. And let's just say this was your empirical formula. You would then take this 4 basically and multiply everybody in that empirical formula by it and get A8, B12, and this would then give you your molecular formula. So once again, that's going to give you basically a number, a factor to multiply the empirical formula by to get to the molecular formula. Now, when we're doing sort of empirical formula and we're dividing by the smallest number of moles, as we talked about, we usually don't want to round unless it's really, really close. The one place where you could be maybe a little bit more lenient in terms of your rounding is this number. So if you get this number and it's not exactly a whole number and it's a little bit more than just above a whole number, a little less than just above a whole number, in this case, for this part of it, you could just round to the nearest whole number. So this is the one place where you can kind of be a little bit more not so careful in the rounding, and you could just round off of that if you don't get a whole number. Any questions on that there? All right. So why don't you try this? The empirical formula of acetic acid is CH2O. What is the molecular formula in this case? In this particular case, we are looking for the molecular formula. So basically, again, the 3 things you need is you need the empirical formula, which in this case they actually gave you, so that's good. You need the molar mass of the compound, which is usually given to you in the problem, and that is this number right here. And lastly, you need the molar mass of the empirical formula. And in this case, we don't have that, so we do need to calculate that. So our empirical formula is CH2O. So to get the molar mass here, again, just adding up the parts, 12.01 for our carbon, plus 2 times 1.008 for our hydrogen, and 16 here for our oxygen. Going to give us here a molar mass of 0.01 plus 2 times 1.008 plus the 16, about 30.03 grams per mole. And we then could take our 60 grams per mole basically and divide it by 30.03 grams per mole. And that's going to get us here essentially a 1.998. That definitely is close enough to round to a 2. And that is the factor that we're going to multiply our empirical formula by. And that will give us C2H4O2 as our molecular formula in this case. Any questions on that there? No. All right, so let's try one where maybe you need to calculate the empirical formula. So why don't you give this one a go? A compound has 1.52 grams of nitrogen, 3.47 grams of oxygen. It has a molar mass between 90 and 95 grams per mole, basically. So it's basically grams per mole. Determine the molecular formula of the compound and its molar mass to four significant figures. So nitrogen 1401 and with oxygen 16 here. So let's take a look again. We want the molecular formula. So three things we need: empirical formula, which we do not have in this case, so we do need to calculate it. We need the molar mass of the compound. That we do have, as that is usually given to you in the problem. In this case, we have a range of molar mass from 90 to 95. And lastly, we need the molar mass of our empirical formula, which obviously we don't have since we have not calculated it yet. So really the first thing we want to do is just the empirical formula sort of problem. We have everybody in grams, so we're going to take our grams of nitrogen, we'll take our grams of oxygen, and really, because we don't have a total mass of the compound or anything like that, we could assume that these are the only two elements involved. We will then use the molar mass from the periodic table to convert them into moles. 1401 for our nitrogen, 16 there for our oxygen. And that will give us here, looks like 0.1085 moles of nitrogen. And for our oxygen, 3.47 divided by 16, 0.2169 moles of oxygen. Once again, like normal sort of empirical formula here, we're going to divide by the smallest, which looks like nitrogen in this case. So we're going to divide everybody by the moles of nitrogen, which is the smallest. That obviously will give us 1 for nitrogen. And in the case here of oxygen, that'll give us basically a 1.999, which again is super close to a 2 and close enough to round. That would give us an empirical formula here of NO2 would be our empirical formula. Now that we have the empirical formula, we have the molar mass of the compound. Now we're ready to get our molar mass of our empirical formula. So the molar mass of this empirical formula, 1401 for the 1 nitrogen, plus 2 times 16 for our 1 oxygen in this case. So 1401, not sorry, 2 oxygen in this case, plus our 2 oxygens, 46.01 grams per mole. So now, as I mentioned earlier, since we do have sort of a range here, what number can we use? Well, we could really, if you want, average the two. You can take 95 plus 90 divided by 2, and you get something like 92.5. So why don't we use that one? So we'll take 92.5 grams per mole divided by our empirical formula there, 4601 grams per mole. And that's going to get us here basically 2.01, which is pretty close to 2. Now, let's just say you did take the low end and you did 90 grams per mole divided by 4601 grams per mole. You will get pretty much the same thing. You will end up with 1.96, which is pretty close to 2. So again, that also is close enough to round. Or if you took the high end, like the 95 here, and you took 95 grams divided by our 4601 times 100, 95, no, times 100, just 95 divided by 4601, you get about 2.06, also close to 2. So regardless of which one you choose, sort of the high end of the range, the low end of the range, or sort of the average value, you will get average value of the range there. You will get pretty much the same answer. So with that being said, 2 looks like the proper factor that we need to multiply this by, and that would give us a molecular formula N2O4 in this case. And if we want the molar mass of this guy, which was part of the question, 2 times 1401 plus 4 times 16 gives us a molar mass of this compound here of about 92.02 grams per mole, which looks like it actually is pretty close to the average value there in between of what we sort of used. Any questions on that particular one? So this is a very common molecular formula type problem where you have to calculate the empirical formula first and then sort of figure out your molecular formula. Any questions on that there? All right, we will lay it up there